This is the fourth in a series of videos investigating the conservation of momentum. In this video, instead of letting two things stick together and move as one, I'm going to let one thing explode and move as different objects. So I've got this mass, and then I've got this velocity initial. Tara, why don't I do this as a capital M? And this is supposed to be a horizontal line, kind of tilted there. I'm gonna let this thing explode, boom. And then out of that comes two pieces of detritus. I've got this mass 1 moving at some V1 final. And this mass 2 moving at some V2 final. Now, I am 100% sure that one of these is gonna go up and one of them is gonna go down. And I will tell you why in just a second. But let's say that I find this at some angle theta and this at some angle phi with respect to the horizontal. Now, I have these two moving in opposite, or one is up and one is down. They're both still moving to the right, of course. But one is going up and one is going down, which is going to invite a two-dimensional consideration. So what we've said in previous videos is that if I'm going to conserve the momentum, which I am here, this is going to have to happen in 2 dimensions. What type of collision is this? Well, that's a little bit of a misnomer because it's not a collision at all, but if you picture time running backwards, right, these two things coming in, meeting, fusing, and then moving as one in the opposite direction, you might be able to identify this as having the flavor, at least, of a perfectly inelastic collision. I'm not going to call it a perfectly inelastic collision. Some people do, some people don't. But it at least has the flavor of a perfectly inelastic collision. So what do we expect? We expect momentum to be conserved. We expect kinetic energy not to be conserved. All right, so I'm going to solve this with the conservation of momentum. I've got still my same momentum equation, not F, I'm looking for P. Total momentum before is equal to total momentum after. So what is my total momentum before? Well, I'm gonna have to be careful. I've already seen that I'm gonna have to solve this in 2 dimensions. So let me do this twice, one in the X direction, one in the Y direction. So in the X direction, what do I have? Well, the initial's all in the X. So I have capital M times V initial. That's before the collision. And then after the collision, I've got this, I've got M1 V1 final, and I need to pick off the X component of this, which I can do with the cosine of phi. And then plus, this is still moving to the right. It has to be moving to the right because the total momentum beforehand was to the right. So I should say the total momentum afterwards in the X direction has to be to the right because the total momentum before is to the right. It's a little bit more precise than what I said. X direction, or X component of this momentum, it's going to be M2 V2 final cosine of theta. So there's my conservation of momentum in the X direction. I would like to call your attention to one thing. I've called these M1 and M2, but let me remind you, I'll come down here. M1 plus M2 have to equal capital N. So sometimes these masses will be expressed to some fraction of the original mass. If they're not, you always can. And that has some value because if you have a capital M in every term, it just goes away and you get rid of your masses. You don't have to do that, of course, but it is always possible to express these masses as some fraction of your total mass before, assuming you've accounted for all of your particles. All right, that's conservation of momentum in the X direction. In the Y direction, what do I have before the explosion? Well, I've got a grand total of nothing, right? There's no momentum in the Y direction. This thing is moving horizontally. So if there's no momentum in the Y direction before, there has to be no momentum in the Y direction after, barring any external impulses. So 0 is equal to M1 V1 final sine phi, that's the Y component here, minus, because this is the Y direction is down, minus M2 V2 final sine theta. That's why I said I was 100% positive that one's going up and one's going down. You can't conserve the momentum in the y direction unless you have something along those lines. You have to have a particle moving up. If you break into two particles, let me say that. If you break into two particles, you have to have one going up and one going down, at least in the y direction, if you had no momentum beforehand. One of these, in other words, has got to be negative, or you have not conserved the momentum. All right, how to proceed from there? Well, you've got, chances are what you're looking for are V2 final and V1 final. So the strategy would be to solve one of these for one of those and plug into the other one, or some way you can eliminate those expressions some way. It doesn't matter how you want to do it. It's up to you. I'll just do it quickly with some sort of substitution here. And I'm going to assume we know the angles. Of course, if you don't, you can solve for those too. Let's assume we know the angles and we're looking for V1 final and V2 final. Let me solve this expression for V1 final. I think that'll be a little bit cleaner than this one since I have a 0 on the left-hand side. So working with this expression, if I move this over or flip them and solve for V1 final, what I'm going to get is V1 final is equal to M2 over M1 sine theta over sine phi, and then V2 final. That's just how I prefer to write it. I prefer to separate like terms. Run through the algebra. Of course, I skipped a couple steps. I would recommend that you run through the algebra. Make sure I'm right, number one. Make sure you know how to do it. And you're going to get something along these lines. We can get rid of this. Bracket that off. I'll put it in sort of the wrong spot. Once I have this value for V1 final from this expression, of course, I can go up to this one and substitute that in. And what I'm going to get is M V initial is equal to M1 times V1 final, all this. I'm going to write the cosine phi. That's these two. And then V1 final is all of this. I'm going to get M2 over M1 sine theta over sine phi, V2 final. That should be a subscript. And then what do I have left? Minus M2 V2 final sine theta. It's getting a little long, but I think we can do it. So looks like we're going to lose this M1 with this one. This cosine phi over this sine phi is going to become a cotangent phi. So I'm going to get, and then let me just write that out. M V initial is equal to M2 sine of theta, left from here, cotangent phi from here, V2 final, minus M2 V2 final sine of theta. Next I need to collect the like terms. Let me move this up. Make sure we're all nice and in frame here. Next, I need to collect like terms. I'm going to get MV initial is equal to V2, let me just write that where we can read it. Capital M V initial is equal to V2 final in both terms, V2 final. What's left here? M2 sine theta cotangent phi minus M2 sine theta. And yep, lost my M1s like I should have. You can pull out an M2 from these if you want to, but now I'm in a position to solve for V2 final. Keep getting my subscript wrong. V2 final is going to equal this term divided by the brackets. What I'm going to get out of that, let me write it like this. Capital M over M2. I'm going to pull out an M2 from both of those. And then V initial over sine theta cotangent phi minus sine theta. And that characterizes V2 final. Of course, once you have that, you proceed like normal. You go back to one of your other expressions up here, or your other expression, I should say. That's all the way back up here. Once you have V2 final, you can plug it in to either one of these and solve for V1 final. I'd probably recommend this one. It's going to be simpler, but that's just some algebra in the future. We have completely characterized the problem at this point, so I will leave the rest of the steps to you. You should complete them just to see what happens.